Good morning to one another. My name is Sisoy. I'm from ECD section, roll number 4J8. Today my topic is about Karnaugh maps. Introduction to Karnaugh maps. In many digital circuits and practical problems, we need to find expression with minimum variables. We can minimize Boolean expression of 3 to 4 variables very easily using K-map without using any Boolean algebra theorems. K-maps can take two forms, sum of product SOP and product of sums according to the need of problem. It means that we can solve your Boolean expressions of 3 to 4 variables and even more such as 5 to 6 variables, which is our topic based on by using K-maps without using more expressions. We can minimize the Boolean expressions and we have types of for K-maps, like we have some of products and a product of sums. It depends on the need for the problem. And the approach for the both techniques will be different. We use one technique for sum of product and another technique for product of sums. K-map is table-like representation, but it gives more information than the truth table. We fill grid at a K-map with zeros and ones, then solve it by making groups. We make a table here first and fill zeros and ones according to the problem, and then we try to pair the groups and then we solve it. Now here we would see the steps for solving the K-maps. First, select K-map according to the number of variables. Identify min terms or max terms as given in problem. Uh, Here min terms and max terms differ. We use min terms for SOPs, that is sum of products, and max terms for a product of sums. For SOP, put ones in blocks of K-maps respective to the min terms, and we should use zeros elsewhere. And this is quite opposite for the POS. That is, for POS, put zeros in blocks of K-map respective to the max terms and ones elsewhere. So here we can see that SOP and POS are having a completely different technique as we have discussed earlier. Now, make rectangular groups containing total terms in power of 2, like 2, 4, 8, except 1, and try to cover as many elements as you can in one group. Here, uh, 2 can be called as duplet, 4 can be called as quadrant, and 8 as octet. Here we should see that mainly more elements of numbers should be covered such that we can reduce the Boolean expression. From the groups made in step 5, find the product terms and sum them up for SOP term. Now let us see an example for K-map of 3 variables, where here the variables are A, B, C, and the problem says that 1, 3, 6, 7. Here we can see that A, sir, we have A is 0, 0, 1. That is nothing but a 1. And we are placed 1 according to the min term SOP, and 0, 1, 1. That is nothing but 3. And we are placing here, and we are having 1, 1, 1, 7. And we are placing here 1 and 1, 1, 0. It is 6, and we are placing here 1. Now we have to make groups of these ones so that we can reduce the Boolean expression which is given. And here we are forming that the red line we can see over here is forming a 2 ones, that is duplet, and the green ones is forming a 1 duplet. And we don't require the dotted lines, dotted blue lines, because both ones are covered in the red group and green group. So we don't require another group which forming the blue dotted lines. This method is, reducing the amount of space and reducing the Boolean expression easily. From we can see that the explanation and the approach is given over here. From red group, we get product term as A dash C. Here A dash C is because you can see that A is constant over here, whereas B is changing from here to here. So we should consider only C. Since A value is 0, we are considering it as A dash and C as C. So the total term for this red group is given as A dash C. And for the green group, we get the product term as A, and here we can see that a C is changing. So we can keep that A is constant and B is constant, whereas C is varying. So we can say that AB. Now summing these product terms, we get final expression as A dash C plus AB. This is for SOP form, where for the POS form, this process of solving is completely opposite, where you have to place ones at all max terms and zeros elsewhere. As we have discussed earlier, we have to place zeros in all the positions where we have placed ones in the SOP form, and zeros where we have placed a map for 6 variables. Below, a 6 variable Karnaugh map aids simplification of the logic for a 3-bit magnitude comparator. This is an overlay type of map. The binary address code across the top and down the left side of the map is not a full 3-bit gray code. So the 2-bit address code of the 4 submaps is gray code. Find the redundant expression by stacking the 4 submaps atop one another shown above. There could be cells common to all 4 maps, though not in the example below. It does have cells common to pairs of submaps. So we can say that the K-maps for 5 and 6 variables will be completely different compared to the K-maps for 3 and 4 variables. And it says that the binary address code across the top and down the left side of the map is not a full 3-bit gray code. Here we can see that completely 6 variable K-map. It says that we have to place ones and zeros accordingly, since it is completely different. Wherever the ABC is completely greater than XYZ, we have to place 1, and elsewhere 0. Here the value of ABC is 1 and the value of XYZ is 0. So we are placing 1 over here, and the value of ABC is 3 and the XYZ value will be 0. We are placing 1 over here. The complete column will be placed like this once, and coming to the 001 of XYZ, since 1 and 1 are equal, we are not placing 1 here. And since 1 comma 1, that is 3, is greater than 1, we are placing 1 over here, and from here we'll be placing all ones. Similarly, all ones are placed like that. Wherever ABC is greater than XYZ, we are placing 1 and elsewhere 0. Now the whole expression for this A map will be AX bar plus ABY bar plus BX bar Y bar plus ABC Z bar plus ACY bar Z bar plus BCX bar Z bar plus CX bar Y bar Z bar. 6-variable Karnaugh map overlay. Now the explanation for the opposite Karnaugh maps is over here. Wherever ABC is greater than XYZ, A1 is plotted in the first line. In the first line, ABC equal to 0, 0, 0 cannot be greater than any of the XYZ value of X. So as we discussed earlier, ABC value of 0, 0 and XYZ value is 0, 0. Since both are equal, we are not placing it anything over here. And coming to the second line, second row, is 0, 0, 1, that is 1, and XYZ value will be 0. 1 is greater than 0, 0, and we are placing 1 over here since ABC is greater than XYZ. No ones in this line. In the second line, ABC is equal to 0, 0, 1. Only the first cell ABC XYZ 0, 0, 1, 0, 0, 0 is ABC greater than XYZ. A single one is entered in the first cell of the second line. The fourth line ABC equal to 0, 1, 0 has a pair of ones. The third line ABC equal to 0, 1, 1 has 3 ones. Thus the map is filled with ones in any cell where ABC is greater than XYZ. Thank you.